So today I'm going to be showing you guys Photon. It's a 2D rendering engine I built in C++. I'm going to zoom in on this text so you guys can see this in the video. I'm going to change a few of these graphics settings. We're going to start out super basic. Now, if you're not familiar with the difference between a game engine and a graphics engine, a game engine is everything that you need to run a complete video game. The graphics engine is the part of the game engine that actually draws the stuff on the screen, the actual rendering. It doesn't know anything about gameplay, it doesn't understand collision detection or physics or anything like that. It just sits there and says, hey, what do you want me to draw? Tell me what to draw. Now this is super basic. I'm not going to use this for anything real. This was just more for educational purposes and partly just for fun. So here's Photon running at its basest level. What I'm doing is using nested loops of set pixel to render colored rectangles to the device context. And as you can see, it looks terrible. It's running at about 4 frames per second. The reason it's flickering is because every time we redraw the black background, it covers the other stuff. And so they're just flipping back and forth. So now I'm going to show you what it looks like when we use buffering. This is the same rendering technique, but instead of rendering right on the display's device context, I'm rendering to a separate device context that's off screen, and then I'm just bit blitting the entire frame over all at once. This is really interesting. For whatever reason, switching from no buffering to single buffering, or maybe this is double buffering, caused us to have an FPS increase. It just about tripled. I can't 100% explain that, but my theory is because we're not making a bunch of separate draw calls right to the device context that's already on display, maybe it's running a little bit faster for that reason. We can also switch this to set pixel V, which is supposedly a little bit faster, but not really. Here's where we're going to see a big difference. I'm going to switch to drawing filled rectangles. "4,000 frames per second. 6,000. Why is it so freaking fast? Because instead of making thousands of individual tiny draw calls for each individual pixel, now we're just drawing 4 things. 3 big rectangles for the background and 1 small rectangle for the player. In fact, let's make this full screen. Okay, we lost some FPS when we went bigger. I think this might be 1024 by 768, but 700 frames per second is still pretty freaking good. The number of milliseconds per frame is almost 0. If we want to see what this would look like with an actual video game, we're going to have to make a lot more than 4 draw calls. Let's mess around with some bitmaps. I'm going to change this to render bit blitting. Not Redner's, that's a grocery store. This is going to use bit blitting for all the graphics. This is the exact same program with the exact same game logic. I even put some scrolling in here so you can see what it looks like when this is moving. When I first started messing around with game development, building my own game engines, I would run the game and everything would be super fast. Then I would have to put a delay in to make sure that you could actually play the game. What would happen then is I would try running the game on someone else's computer and it would be either too fast or too slow. The speed of my game was completely dependent on the computer that I had built it on. I started putting timers in my game. I would force the game to run at 30 frames per second. But that's not necessarily always the best idea either. Why would you want to limit how fast the game renders? For this game, I separated all the game logic into two categories. First category is frames. These are things that we want to have happen as fast as possible. Second category is steps. Frames have unlimited speed. Things like rendering and getting input from the keyboard. What kind of things do you want limited in your game engine? Things like the game logic. Here's what it looks like if you don't limit the speed of the game logic. It's way, way, way too fast. Imagine if the AI was moving that fast. No human could possibly play this game. I'm going to show you some of the rendering code. I'm just going to scroll through this pretty quickly. Here's the final bitlet, where I'm moving everything from the buffer to the main device context. These are the actual images I used for this little test demo. It's just a big bitmap background, bitmap player, and the player's mask. Now the mask is important because that's what gives us transparency. That's why you don't see a big white box around the player as he's moving around. The way we get that is we actually draw an inverted player, then the mask, then the inverted player again. There's 3 draw calls. I'm going to line them up horizontally and show you guys what that looks like. So these are the 3 sprites we're actually drawing. It's the player with inverted colors, then the mask over top of that, which gives us back our background, and then the inverted player on top of that, which double inverts the colors and we get regular Richard back again. So that's pretty much it. I'm probably not going to do anything else with this. There's no reason for me to be writing my own rendering code when DirectX already exists, and OpenGL, and Monogame, and all these other graphics engines. I just did this for fun. It was a really cool learning experience. Let me know in the comments if you guys want me to explain any of this stuff more in depth or give you more of a real tutorial on how to do this. See you next time.